So let's get started. So welcome back to CS267. And today we have a guest lecture by Brian Catanzaro, who's an expert on using GPUs. He's a graduate student in the Parlab. And this is important because this is the first semester we're actually going to have a GPU programming assignment. So in your homework assignment 2, the second part of it will involve CUDA programming. So thank you, Brian.
Great. And I don't know. I still don't know if it's on, but
yes, no.
Okay, great. So I'm glad to be here this morning. Like Jim said, my name is Brian Catanzaro, and I'm a grad student in the Parlab. I see a few familiar Parlab faces amongst the crowd, but most of you I don't know. So I hope you enjoy learning a little bit about GPUs and have fun with your programming assignment. So I'm going to start out just by introducing some terminology. I find that in today's day and age, when parallel microarchitectures are proliferating in all sorts of different ways, that the terminology becomes pretty inconsistent and it can be confusing, especially when you're trying to learn exactly what these things are that we're going to be programming and how we're going to be programming. So I'm going to just establish some terminology that makes sense to me and talk about the various hardware features that we're going to be using when we program GPUs. Then I'm going to talk about the CUDA and OpenCL programming models, and then I'll talk about how CUDA programs are actually mapped onto NVIDIA GPUs, which is important if you're doing performance tuning, and I'll also mention OpenCL. And I'll finish up with some little anecdotes, if we have time, about some of the projects that have been going on in my research group using GPUs to do interesting things. So to start out, I like to throw up this slide about the difference between multicore and manycore architectures. Seymour Cray, who was the founder of Cray supercomputers, which were really important back when I was a child, but I don't know, I might be a little older than some of you, so I don't know how familiar you are with Cray. But anyway, he came up with this analogy that, would you rather have a flock of chickens or a yoke of oxen to plow a field? And actually, I think most people would like the yoke of oxen, right? Like, a few really strong oxen can get a lot of work done. But if you're trying to pluck all of the worms out of a field, you might as well use a flock of chickens, right? And I think this is kind of a silly little analogy that encapsulates the difference between sort of the two strands of parallel microarchitectures that I think are out there today. We have sort of the yoke of oxen approach, which I call multicore, which is you have some assemblage of a few cores, each of which are a descendant of a single core that used to take up a whole chip and is designed for really high single-thread performance. And then we have Manycore, where we've decided to, if we're going to go parallel, we might as well go parallel all the way. So who cares about single-thread performance? What we really care about is the aggregate performance of all the cores on our chip. And we're going to sacrifice single-threaded performance by maybe 10 or 50x compared with a traditional, strong core. The reason this is important is because the programming models are different. When you program multicore, the traditional way that people do that is using things that evolved from the threading models that people used to program single-threaded cores back when those were all we had. With Manycore, because we need so much more parallelism to fill a chip, the programming models are going to be different, and that's why GPU programming models are the way they are. And to motivate this just a little bit further, I like to show pictures of actual chips, keep us grounded here. So on the top, we have an Intel Westmere EP. It's a 32-nanometer device, and it has 6 cores. And we can actually see the 6 cores in this die photo. They're sort of in vertical slices up on the top. You can see the 6 banks of last level cache here on the bottom. And you can see that each of these cores is pretty big. In contrast, we have here a picture of a Fermi chip from NVIDIA, which has 16 cores, and each one of these cores is one of these little boxes in here, and then the stuff in the middle is basically the crossbars and so forth needed to tie them all together, plus some graphics functionality, which I don't actually use when I'm programming these things. So that's kind of the overall picture of what they look like. And so let's talk about some of their parameters. So the West mirror has 6 cores, each of which can issue 2 SIMD instructions per cycle, and each of those SIMD instructions is 4-way. So if you multiply all that out, it's 48 sort of SIMD lanes that it can execute per cycle. Yeah. Right. So you guys in your matrix multiply assignment were using SSE. Is that right? So you're familiar with SSE intrinsics, where you perform a multiply for every lane. So SIMD, the SIMD width of SSE is 4, right? And so that's what a SIMD lane is like one of those lanes in a SIMD vector. Okay, so also the West mirror is running at almost 3.5 gigahertz. Intel has a wide variety of different processors. I've chosen the West mirror to put up here because it has one of the highest peak floating point rates that Intel has out there. They do have chips with more cores, but their clock frequency is quite substantially lower. So, all right. So let's see. What else should we say? The Fermi, which is I'm looking at the GF110 incarnation, which just came out a few months ago, has 16 cores, each of which are also can issue 2 SIMD instructions per cycle, and each of the cores has a 16-way SIMD unit, and it's running at 1.5 gigahertz. One of the big differences is the amount of threading that each of these cores is built for. So I said earlier that the West mirror, each core has 2 threads, so it's it's switching. It's actually running in simultaneous multi-threading 2 threads on each core. The Fermi actually has 48 threads per core. So the amount of parallelism that you need to fill a Fermi chip is actually really big. You need about 25,000 SIMD lanes worth of parallelism in your program in order to fill the chip and keep it running. In contrast, on the multi-core chip, you need like 48. So there's a difference of about a factor of 50 there. And let's see, the performance is also different. So the multi-core chip has about a factor of 10 less floating point throughput. It has about a factor of 5 less memory bandwidth. And the memory hierarchies are very different. On the Manycore chip, because it has so many threads that it's trying to keep in context on the chip all the time, in order to hide memory latency, it needs to have a lot more storage in the register files. So the register file is really big compared with a traditional multi-core chip. And the caches are much smaller than the multi-core chip. So it's really nice to have a 12 megabyte L3 cache on this multi-core chip. The Fermi only has a 3/4 megabyte cache. So the way that you program these things is going to be really different. All right, so now that we've established what kinds of chips we're looking at here, let's talk some more about terminology. So what is a core? This is kind of a contentious question. The marketing departments, especially of all the various companies, have their own definitions. Some people think that a core is equivalent to like a floating point unit, right? So, or an arithmetic logic unit. So ATI will tell you in their marketing literature, oh, our chip has 1,600 streaming processors on a chip. 1,600. Wow, you're like 1,600 cores. That's a lot of cores. Well, it turns out that the way they get at that number is that they have 20 SIMD cores, and then each of those is 16-way SIMD, and then each of those SIMD lanes is actually 5-way VLIW, so you multiply it all out, and you get to 1,600. So that's one way of looking at it. NVIDIA will tell you that their GF110 chip has 512 CUDA cores, which actually means they have 16-way SIMD times 16 multiprocessors, what they call, and then times two-way multi-threading. So I want to sort of orthogonalize all of these different microarchitectural parameters from the actual way that we think about programming these chips. And so I use the word core more consistent with the CPU world. And so I would say that the AMD chip, instead of having 1,600 cores, I would say it has 20. Instead of 512 cores on the NVIDIA thing, I would say it has 16. And this matches up well with, Intel, who will say that Westmere has 6 cores instead of, 48. If they were multiplying all this stuff out, they could get to some larger number too. But that's just confusing. So, so that's what we're going to say is a core. And we're also going to talk about SIMD. So I just asked you about SSE, so you guys are familiar with SIMD already. But I want to point out a couple things about SIMD. The reason that we care about using SIMD, why it is widespread, because it does make programming more difficult. The reason why we care is because it's more efficient in terms of power especially, and also in terms of area. We're trying to amortize the control overhead of running instructions over multiple copies, right? And so this gives us efficiency, but it exposes parallelism to the programmer and the compiler. And I'd actually like to claim that SIMD is a form of neglected form of parallelism. When people talk about parallel architectures, most of the time people talk about MPI or they talk about pthreads. They talk about programming models which are targeting a core but not a SIMD lane. And one of the reasons for this is that it's difficult to automate, right? It's hard for a compiler to exploit SIMD because you have to make sure that you're executing something that's the same on all these SIMD lanes in order to issue one of those instructions. And a lot of languages are really difficult to vectorize. So the most common solution that people have used over the years is basically three different ways of dealing with SIMD. One is to just forget about it and say parallelism is about threads. It's not about SIMD lanes. We're just not going to worry about it. And Intel has a great auto-vectorizing compiler, and maybe it will do something useful. And you sort of just cross your fingers. And that generally doesn't work. When I worked at Intel, everybody in my group that was writing code that needed to use the SIMD capabilities of the processor would write using intrinsics instead of trusting the vectorizing compiler, because the compilers, it's just, for whatever reason, it's a hard problem and it just doesn't work as well as we'd like. So that's the second approach, is instantiating intrinsics, which I'm guessing you did some of that in your last homework assignment. And that lets you use SIMD very effectively, but it's pretty low level, right? You're kind of writing almost assembly language. And it requires you to rewrite it every time you have a new processor with a different SIMD extension. And there have been a lot of different SIMD extensions over the years. Let's just look at x86, for example. It started out in the 90s with MMX, which was 8-way SIMD with 8-bit integers. Then they moved to SSE, which was 4-way 32-bit single precision floats. AMD was impatient with Intel because it took Intel a long time to go to SSE, so AMD made 3D Now, which was also a 4x32-bit single precision floating point SIMD extension set. But it got discarded when Intel made SSE and moved on. So everybody who coded for a 3D Now, they had to kind of just abandon their code that they had written. Similarly, if you wrote for MMX and then you wanted to take advantage of SSE, you had to throw away your code. SSE became SSE2, where we added double precision and made things more general, more flexible in general. Then it went to SSE3, and then supplemental SSE3, which is a mouthful to pronounce. AMD went off again with SSE 4.8. And AMD is coming out with SSE 5 this year, or at least that was the plan at one point. I'm not sure if they're still doing that. Then Intel went to SSE 4.1 with Nehalem about 3 years ago, and then SSE 4.2, and then AVX, which is the latest one, which is 8-way 32-bit floats or 4-way 64-bit double precision floating point. That just came out a few months ago. So we are now, in this history of x86 SIMD, we're now right here. Although most of the machines, I don't think any of the machines in your lab actually have AVX yet, but you can actually buy them. Okay, so why did I present this scary slide of all of the history of different SIMD? Well, it's because of this programming problem. You know, how are we supposed to take advantage of it? SIMD changes all the time. We don't want to have to rewrite our code all the time. And it turns out that the first solution, which is the most common one of just doing nothing and hoping the vectorizing compiler does something, and it usually doesn't, that used to make more sense than it does now. And the reason is because SIMD is getting to be such a high percentage of the throughput of these multi-core processors. So, you know, back when we had just 4-way SIMD, let's say that we didn't use any of the SIMD and we just ran it in scalar mode, well, we'd be throwing away 75% of our performance and maybe, you know, at best getting 25% of peak performance. Well, you guys tuned matrix multiply. 25% of peak performance is actually not so bad, right? Like, I mean, when you started out, what kind of numbers did you get when you were tuning matrix multiply? Your first naive code. Anybody want to tell me? I mean, there's no shame in this, right? Like, if I sat down to do it, I'd probably get like 3% of peak, right? Anybody have any experience they want to share with that? It's too early in the morning. Oh, it's not, well, it's not due till tomorrow, but I hope, you know, at least somebody has started it, right? I'm not asking for what they finally got at the end of the project, but yeah.
I think the code, the starting point was 5 or 10%.
Okay, so the starting point was 5 or 10%. You know, and to be honest, most code is not matrix multiply, right? Most people are not going to spend, I don't know, a week or 2 weeks optimizing a 4-line C program, right? And so if you're being limited by 25% of peak, actually for most codes that's totally fine, right? It doesn't really matter. Well, the problem is that when SIMD becomes more and more of a fraction of the performance that your machine actually has, then it becomes a lot more expensive. You know, so with Larrabee, which is an HPC card that Intel has been thinking about for a while, it has 16-way SIMD. It's an x86 chip with 16-way SIMD. You know, if you don't use the SIMD, then you're limited to 6% of peak. And you know, you can see where this is going, right? Like that, the more we rely on SIMD, the more the programming models are going to need to support SIMD. And the previous way of using SIMD, which is do nothing, that's not going to work because we're really going to throw away too much performance. Or instantiate intrinsics, that's also not going to work. I just showed you a really scary slide with 20 different SIMD variations, each of which requires a complete code rewrite. So that doesn't work. So we need some programming model that's going to deal well with SIMD. In addition, we also need a programming model that composes well with thread-level parallelism because we now have multi-cores or many cores. So this is kind of setting the stage for why GPU programming models are the way that they are. Because we need something that deals with many different kinds of parallelism, and we can't neglect SIMD. So the CUDA programming model came out in 2006. At the end of 2006, it came out in beta. So it's not been around for too long, but it has been fairly successful in exploiting many core architectures, wide SIMD parallelism, and creating scalable binaries that can run all the way from very small chips to very large ones. And the way that it works is CUDA provides a thread abstraction that deals with SIMD parallelism as well as traditional core-level parallelism, and allows you to perform synchronization and share data between groups of threads in a hierarchical thread model. CUDA programs are actually written in C or C++ with some minimalistic extensions. I'd like to point out, so the question is, how relevant is CUDA to you? CUDA is a project from a single company. It comes from NVIDIA. the world is much bigger than one company. So OpenCL, which was a project which Apple was basically the one responsible for, it is a project that basically takes the lessons from CUDA and applies them in a vendor-neutral way so that you can program any parallel architecture using the same kinds of ideas that CUDA has. And I'll be talking about that also. But once you understand the CUDA programming model, you pretty much understand the OpenCL programming model. So I'm just going to explain things from the CUDA perspective, and then we'll translate to OpenCL terminology. So the idea is that we write programs using a hierarchy of concurrent threads. We write a kernel, which is going to be some parallel function invocation. And this kernel is going to be composed of many threads. Like I said before, it takes on the order of 25,000 threads to fill up a Fermi class machine, a single chip. So we're going to write programs that have tens of thousands, hundreds of thousands of threads. And all of the threads are going to execute the same sequential program. So basically, it's a parallel function launch. We're going to launch, a million of these things, and they're all going to do the same thing. Of course, we can branch in these programs, and so although they may all start at the same place, they might not all do the same computation. But the way that we initially get things going is with a parallel function launch, everybody doing the same thing. Threads are grouped into thread blocks. Now, the concept of a thread block is sort of like a team. It's a group of threads that are going to be scheduled onto the same core, and they're going to be able to synchronize with each other and share data with each other. So the thread block is kind of like the atomic unit of a CUDA program in the sense that thread blocks are going to, once they start, they're going to run to completion. They're going to it's sort of the scope in which you're going to think about sharing data between threads. Sharing data outside of a thread block is actually very hard and limited. There are limited ways of doing that. And the reason for that is scalability, which I'll talk about in a little bit. CUDA is also similar to a single program, multiple data kind of programming model. Every thread in a CUDA program has a unique identifier that you can query in your program, and every block also has a unique identifier. So you can say, like, what is my thread index? And then you can say, if my thread index is less than something, then do this, otherwise do that. So that's the mechanism that you can use to sort of figure out where you are in your parallel function launch. So what is a CUDA thread? It's an independent thread of execution. It has its own program counter, so all of the threads can branch to do their own thing. For performance reasons, you might not want to do that, but it's nice to have the flexibility to write programs where all of the threads can potentially do different things depending on what the data requires them to do. Each thread has its own set of variables, which are kept in its own private set of registers. However, there is no implication in a CUDA program about how threads are scheduled. In particular, there's no implication that CUDA threads are scheduled in a fair manner, meaning that if one of the threads is blocked, then another thread for sure will be able to make forward progress. And all the threads will be able to make forward progress until we, reach some synchronization point and then continue on. In fact, CUDA allows for, and NVIDIA's implementations of CUDA, how CUDA programs are actually executed, have a very unfair thread scheduling mechanism, which is different from what you might expect running p-threads on a traditional multi-core system with an operating system that tries to guarantee you fair thread scheduling. And I'll talk a little bit about what that means in a second. So CUDA threads might be physical threads, like on NVIDIA graphics processors. Each CUDA thread is mapped directly onto a hardware thread. They might be virtual threads. For example, there are CUDA implementations for other things besides NVIDIA GPUs, they're all kind of research projects right now, so nothing that you could really use. But you know, there have been announced plans to make CUDA run on things other than NVIDIA GPUs, where you might want to map things differently. So you might want to say, instead of one CUDA thread becomes one hardware thread running on an x86 multi-core chip, instead we can make one CUDA thread block a hardware thread, and then we can sort of have a for loop that is going to iterate over the different threads in the thread block inside of this thread running on a multi-core. So the way that threads are implemented is not actually part of the programming model itself. And we talked a little bit about thread blocks before. I just want to revisit them. So a thread block you can think of as a virtualized multiprocessor. So when you launch your code, you don't have to think about, like, okay, how many cores do I have? Well, I'm going to launch exactly as many thread blocks as there are to fit the number of cores that I have on my machine. So it's virtualized in the sense that you can decide, well, my data has 1 million elements, and I'm going to group my data into groups of 256 elements and run a thread per element. And so in this function invocation, I'm going to pretend as if I had 1 million over 256 cores that I'm going to launch these thread blocks onto, as opposed to, you know, the opposite, which is kind of the traditional way that people program multi-core systems, where the first thing you do is take the number of data and you divide it by the number of cores that you want to map it onto. Another way to think about thread blocks is as a data parallel task. So like I said, all the blocks in the kernel have the same entry point because we're doing this parallel function launch. But once we start, we can have all of the blocks do whatever they want. So you could do things like, I want the first half of the thread blocks in my kernel to run program A, and I want the second half to run program B. And there's no performance penalty for doing that. If you have different thread blocks running different programs, because the hardware is, you know, very MIMD. I showed you the die shot, and there were 16 cores on it. Each of those 16 cores can be doing different things. It's no problem. So you can think of a thread block as a data parallel task. However, they have to be independent tasks. Like I said, you can't synchronize thread blocks modulo some weird caveats. But the best way to think about it is that they're completely independent. You can't synchronize them. And your program has to be valid for any interleaving of block executions. And in particular, that means that you can't make the assumption that any two blocks are going to be concurrently executing on the hardware at any time. So you can't write a program that has like block A and block B that want to share data. Maybe block A is producing data and block B is consuming data, and you want to enforce that both of them are co-resident and working together cooperatively. That isn't going to work. If you want to have producer-consumer style relationships, they need to be within a thread block, not between thread blocks. Because otherwise, this assumption that your program that has to be valid for any interleaving of block executions is not valid, because if block B is running and block A has not been scheduled yet, block B will just be sitting there waiting for block A to give it something, and block A may never be scheduled while block B is alive. So that's a fairly strong restriction. Okay, so I want to map these concepts back to sort of the kinds of parallelism that maybe you've been talking about in the class at other times. So, you know, what about thread parallelism? How does that show up in the CUDA programming model? Well, basically, you can think of each CUDA thread as being an independent thread of execution. Data parallelism, how does that show up in the CUDA programming model? Well, across threads in a block, you often map your threads onto your data, and you often map your blocks onto your data. So it's a very natural data parallelism model. Task parallelism is a little bit more challenging in the CUDA model. We can have task parallelism in the sense that different blocks are running different tasks. But task parallelism also usually implies a method of synchronizing and exchanging data between concurrent tasks. And we actually don't allow much of that in CUDA, because the tasks have to be very independent. The way that you get actually synchronization and data sharing between tasks in CUDA is with a barrier. And I'll talk about that in a second. basically end the kernel and start a new one. Okay, so talking about, and this is exactly what I was just saying. So talking about different kinds of synchronization. So within a block, the threads can synchronize with a lightweight barrier. You know, if your threads are already sort of running together, this barrier is really cheap to execute. You're doing something, you sync threads, and then you do something else. The sync threads, not only does it synchronize all of the threads to the same point of execution, but it also ensures memory consistency, that all the threads in the block can see all of the writes that the other threads in the block have made up to that point. So this is useful, for example, if you have two threads in a block that need to exchange data. You know, it's not just enough for both of them to get to the same point where they're waiting to exchange data, but the writes that they've made to the memory subsystem actually have to be visible to each other. And the sync threads actually guarantees that. So blocks may coordinate. We're talking about how different thread blocks can communicate. Well, I said that they can do so only in very restricted ways. This is the main way they can do it, using atomic memory operations. So for example, let's say that we have a queue, and we're going to run all these thread blocks, and each of them is going to put out a variable amount of data. After doing some work, they're going to figure out, I need to stick, I'm going to produce 3 items this time, and then another thread block might decide, I'm going to produce 10 items this time. So you can use atomic memory operations to sort of coordinate how each of the thread blocks is outputting their data. So you could say, you could have a shared queue pointer that's pointing to the end of a queue, and each thread block is going to increment that with some atomic operation and get back the address where it should store its results, despite the fact that all of the blocks may be outputting a very different number of data items. So this is a certain kind of coordination, right? Because the blocks are actually interacting, but it's not going to. It's not like a full synchronization and communication. We're just talking about an atomic memory operation on a very small piece of data. And then, like I said just a second ago, there are implicit barriers between dependent kernels. So this is the syntax, and I'll talk about this in a second, but at the bottom you see the syntax for launching kernels, and here I'm launching 2 dependent kernels, and there is going to be an implicit barrier which requires that the entire function call to this first function is complete, and all of its results are visible in memory to anything else that might want to use them before we start the next one. And so that's how we get barriers at the kernel level. Okay, and I've sort of covered this, so I'm going to skip that slide. The reason why CUDA has all these restrictions on how thread blocks can communicate is because we want to write scalable parallel programs. So the very same CUDA program can run on a GPU that has 1 core, or it can run on a GPU that has 30 cores, and it should be getting good performance on all of those various processors. And if you write your code and it presumes that it has 16 cores to work with, and then you try to run it on a machine that only has 2, that can be problematic. Also, the other way, if you write your code that presumes 16 cores and then you run it on something with 50, you can be significantly underutilizing your machine. So CUDA forces you to write scalable programs in the sense that you can't map it directly to the hardware. So so you end up with a binary that can run on a variety of hardware. And that's a good thing. All right, so the hello world of CUDA programming is probably vector addition. So what we're going to do here is just compute the sum of 2 vectors. And we're going to map 1 thread onto every element of the 2 input vectors, and each thread is going to produce 1 output element. So you'll notice the arguments. So the first thing to notice is this global decorator. The global decorator means that it's going to be running on the GPU, and every global function has to return void. So, yeah. Yes, right. So CUDA programs are for a heterogeneous system. I'll talk about this in a second, where you have a GPU that is coupled to a host, and the host will do things like, I/O, deal with visualization, and so forth. So the decorators that we have actually help the compiler know which part of your program you're intending to run on the GPU and which part you're intending to run on the host. So if you'll notice, because every global function, and this is an entry point, this is something that you can call from the CPU, has to have a void return. That means that the results, what are you going to produce, has to be pre-allocated and is also one of the arguments to your function. So in this case, the output is a vector that I'm calling C, and it's just another input to the function. So the first thing that we do in this function is we figure out which thread we are. So we do that by looking up what the index is of our thread block, and we multiply it by the dimensionality of our thread block, and then we add our thread index within the block to come up with our global thread ID. Now the .x's on all of those are just a programmer convenience. You can make thread blocks and grids, which are the configuration of the thread blocks. You can make those in different dimensionalities. They can be two-dimensional. Thread blocks can be three-dimensional. There are certain restrictions on the sizes of things that you can make, but ultimately this is mostly for programmer convenience. So for example, if I'm doing a vector add, it's kind of a one-dimensional problem. I'm just going to use a one-dimensional thread block and a one-dimensional grid. If I was doing some image processing on a two-dimensional array, it might make more sense for me to do a two-dimensional block and a two-dimensional grid, in which case my index would be a function of blockindex.x and blockindex.y and so forth. Okay, so then the next function is just the thing that launches it on the CPU. So this is just some host code. And I've stripped out a lot of the details, which I'll get to in a second, about how memory is managed between these. But what I want to point out is the syntax for actually launching one of these functions on the GPU. You name the function that you're calling, but then there's this triple chevron thing. And what that is the grid and the block configuration that you want to have when you launch this function. So here I'm saying that I have some number n that's the length of my vector. I'm going to divide it by 256, and that's how many thread blocks I'm going to launch. And then each of my thread blocks has to be 256 elements wide. So what kind of assumption did I just make on n? Right. So I just made the assumption that n is a multiple of 256. What would this code do if I ran it on something that n was not a multiple of 256? Exactly. It would be a segmentation fault, which on the GPU is even worse than on the CPU in terms of inscrutability. So it would actually look like a CUDA launch failure. Michael.
Actually, since integer divide does a floor, wouldn't it just not add the tail of the vector?
Well, so it would not add the tail. Let's see. Yeah, that's probably true. Yeah, so it might be safe, but we're playing it fast and loose here, right? So this is a technicality that Michael pointed out. Yes, because integer divide does do a floor here, so we'll probably be safe. But in general, CUDA code, you need to be careful about sort of these sort of overrun problems. So let's say that you actually wanted to run it on a vector that was not a length of 256, not a multiple of 256 elements. What you'd want to do is sort of encase this computation in a conditional that ensures that your global index is actually less than the length of your program, so that you make sure never to access memory that doesn't exist. All right. So memory models. CUDA has an idea of per-thread local memory that is private to each thread. That you don't really use when you're programming CUDA programs very often. It's sort of mostly used for the compiler for spilling and filling register files and things like that. So it's not something that enters into my mind when I'm doing CUDA programming very often, but it does exist. And it's implemented in slow off-chip DRAM. There is per block shared memory. For every block of threads, there is the ability to use what NVIDIA calls a shared memory. This is a structure that is intended to be fast. It's on chip, and it's where you want to communicate between threads in a thread block. Then we also have the global memory, which is off chip and much slower compared with shared memory. We're going to be running kernels in sequence, and they're going to be reading and writing from this. The data that they create will persist across kernel invocations, so you can, so it's very common to produce data in some form. Then when you need a synchronization, you end the kernel, and then you start another kernel that is going to be processing the results. And then also we need to talk about the heterogeneity here, because we are running a program on the host as well as on the device. Data to and from the GPU is handled with explicit mem copies that are going to be moving data back and forth. And in the standard case where you just have one GPU, you just have sort of this device 0, the CUDA mem copy, you don't even have to specify exactly which device you're going to. So most of the time that won't be a problem. But I do want to show you what it looks like to actually use these things on the host. So here's the main function that I sort of threw a lot of details away before when I was looking at it. So let's declare n as some multiple of 256, and then we will malloc data on the host that is sized appropriately. So we're going to make A, B, and C on the host. We also want to make A, B, and C on the device. And so the way we do that is we declare float pointers. They're just float pointers like anything else, but when we call malloc, we're going to call CUDA malloc, where we pass a pointer to the pointer and then tell it how many bytes we want. And that will allocate space on the GPU and return us a pointer that we can then use as an argument to a function that we're going to run on the GPU. However, before we actually do that, we're going to want to make sure that the data that those pointers actually represent has been initialized. And so we're going to do some CUDA mem copies. And this is all in the documentation, so you don't have to remember the syntax for this. But just the sort of the things that go in here are the destination pointer, the source pointer, the number of bytes that we're going to be copying, and then the directionality of the copy. So there are 4 different directionalities. Here we're using the one where we go from the host to the device, which basically says stick that on the GPU. Okay, and then we call our vector addition here, and then we do the CUDA mem copy in the reverse direction, where the destination is the host pointer coming from a device pointer, and we go we have the appropriate directionality argument here. So that's going to actually take care of moving the data back and forth on the host. Now there is another thing that I'm just going to briefly mention. I'm not going to go into detail with, but CUDA function calls, function launches are asynchronous. So if you want to queue up a whole bunch of different kernels on the GPU, when you run this on the host, it's just going to basically stick a function call on a queue that the GPU is then going to start processing. But it's going to return immediately before the work has actually been done. So that means that there are barriers that you need to have in your code, especially if you're trying to time something, right? If you have a loop that does this vector addition 1,000 times, and you want to then time that loop and divide by 1,000 to get the time for each of the loop iterations, well, you're going to be in trouble because you're not actually going to measure the execution time at all. You're just going to measure the time it takes to put a function call on the queue 1,000 times, and that's not actually what you want. So there is a function call called CUDA thread synchronize which you would then put after that for loop, which would ensure that all of the things that you've asked the CUDA runtime to do are completed before letting the host code continue. And there is an implicit CUDA thread synchronized before any mem copy from device to host. So in this case, since we're trying to take data from the device, we don't actually have to put a synchronize in here to make sure we get useful results. That's just the CUDA default that there will be a synchronize there. But it's something to keep in mind that, that CUDA function calls are asynchronous. Okay, so how do we use shared memory? I'm going to talk about this in great detail later, but memory considerations dominate Manycore programming. So one of the most important things that we have to do when programming any of these parallel devices is think about how we're using our on-chip memory resources. So this is definitely something that I spend time thinking about when I do CUDA programming. So to declare a pointer that is referencing on-chip memory in CUDA, you use this shared decorator. It can either be like just a pointer here, in which case no space will actually be allocated, or you can allocate space using an array declaration. You can also allocate a dynamic amount of space. So the downside of using this syntax to do this is that the amount of data that you're asking for has to be known to the compiler, right? This block size, because C arrays, they have to have a constant size when you declare them. If you want to have the amount of shared memory depend on the particulars of the program that you're writing, you can actually, there is a way of doing that. It's dynamic shared memory allocation. I'm not going to tell you the syntax, but it just ends up being another parameter that you put in that triple chevron with the launch syntax. So you say, I want my thread block to be this big, I want my grid to be this big, and I want each of my thread blocks to have this much dynamically allocated shared memory attached to it. So one of the most common idioms for using shared memory is to communicate between threads. So often what you'll do is so for this example is a really simple example where every thread has loaded some data and put it into Scratch based on its thread index, and then we synchronize so that all of the data is populated in shared memory, and then, for example, we could grab the element from the thread to our left. That's a very common idiom where all the threads in a thread block put something into shared memory, then we synchronize, and then we pull out something that we didn't compute ourselves. And the performance implications, shared memory is faster than the L1 cache on Fermi class devices. It's slower than the register file. And it's relatively small. So shared memory can either be 16 kilobytes per core, or it can be 48 kilobytes per core. And there's a trade-off with the amount of L1 cache that you get there. And the register file is much bigger than that, which means that you don't use shared memory to store data as much as you use it to communicate. It's actually better to use the register file and store data in registers than it is to store it in shared memory. Shared memory is actually a more valuable resource. And so the right way to think about shared memory is a place to communicate between threads. Yeah?
So maybe you could contrast that, we're used to thinking of caches being nested, and that's not the case here. All the different memories are not nested.
Well, right. So the memory hierarchy is complex. Shared memory is not nested. Every core has its own block of shared memory, and it's all programmer managed, right? So in order to use shared memory, you have to populate it first, which is, for example, in this code, what we're doing, where every thread is, sticking something in there, right? You can't just load the data and then expect it to magically appear. That's how a cache works. That's not how a scratch pad like CUDA shared memory works. On the other hand, current GPUs now have the beginnings of caches as do normal CPUs. So the shared memory is partitioned between the block of memory that comprises shared memory is partitioned between shared memory and L1 cache. It's the 16K, 48K split. You can have it either 16K of shared memory, 48K of L1 cache, where all of your reads are going to be laying around in the cache in the hopes that maybe you'll use them again. Or you can have it the other way, where you have 48 kilobytes of shared memory and 16 kilobytes of L1 cache. The L1 cache is useful, for example, for spilling and filling registers in your program. If the register state of each thread is larger than what the register file can handle, then the compiler will insert loads and stores for those data values into the cache, and hopefully the cache can help out with things like that. But I might be getting a little ahead of myself there. So, all right. So a little bit more about the syntax of CUDA. It's designed as a minimalistic extension to C and C++. So we have these little decorators. Global means that if you decorate a function with global, it means it's a kernel that you can call from the host. If you decorate a function with device, it is a function that you can call from a global function. So this is a sort of a function call that you can make from within a GPU function. You cannot call a device function from the host. That's illegal, and the compiler will tell you so. Absolutely. You can call device functions from device functions, and on Fermi class machines, device functions can also be recursive and so forth. So yes, we have, you can also use these decorators on data in certain ways. So if you declare, for example, an integer as a device integer, that becomes a global variable that all of the functions within that file scope can access. And we already talked about the shared decorator, which creates shared memory for per block shared memory. We also talked about this triple chevron. This is how we talk about parallel kernel launches. And then there are a few intrinsics. So some intrinsics that are used for identification are these thread index, block dimension, and they're declared as this dim3 type, which has a .x, .y, and .z field that you can access to get the different extents of the dimension. Yeah?
Can you put extern when you have extern on the global variable?
I believe you can. I believe you can put extern on a global variable. I've never tried that just because I don't like global variables. But I have, yeah. There have been file scope issues in the past. So CUDA started out kind of as a garage project, and NVIDIA is a GPU company. They make things to play games with, and the maturity of the compiler has been an ongoing development. There are a lot more things working like that now than used to be. So I wouldn't be surprised if the particular issue that you're talking about now has been resolved. But yes, there have been a lot of weirdnesses with things like that. And then there are other intrinsics, like, for example, sync threads and thread fences. So a sync threads is a barrier where all the threads proceed to some point in the program, and then they all make sure they're at the same point in the program. And it implies a thread fence in the sense that all of the threads in the block, all of their memory writes have to be visible to other threads in the same block. However, there's also thread fence intrinsics, which can be used, for example, to ensure that all of the writes made by a thread are visible to all of the other threads in a block or all of the other threads on the machine before continuing. So if that's interesting to you, they do exist. And CUDA GPUs have double single precision that support denormalized numbers and good rounding modes that IEEE mandates, as well as the standard math functions that you would expect, and a series of atomic memory operations that we've talked about before. Yeah?
So on the previous slide, I guess you're saying CUDA is like Fortran 4 because it only has three-dimensional kind of arrays, if you like.
Well, so the DIM3 that I was showing before isn't actually connected with arrays, right? You can make arrays of any dimension that you want, but it is connected with the dimensionality of thread blocks and grids, and those are limited to 3 dimensions. In fact, they're even more limited than that. Grids can only be 2-dimensional as of today, even though they use a dim3 to represent it. But if you try to stick something that's non-zero in the z dimension, then you'll get a kernel launch failure. Also, there are restrictions like, things like, okay, so X, Y, and Z for thread blocks can be maximum 1024 for X, Y, but then for Z it has to be maximum 64, and X times Y times Z has to be less than 1024. So there's all sorts of little weirdnesses like that. At least for when you're compiling CUDA to GPUs. Of course, if you were compiling CUDA to something else like OpenCL does, the weirdnesses are completely different. And then there's a variety of CUDA runtime functions that you also need to use. Explicit memory allocation, and don't forget to free your pointers after you use them. That's good habit. Explicit memory copies. Then there's some more graphics-y things like textures, which graphics chips have texture caches in addition to normal data caches. They are designed for particular access patterns that are commonplace in graphics. And if you want to use them in CUDA to see if it helps, you can. It's complicated, but you can do it. You can interoperate with other graphics APIs so that you can visualize what the results of a CUDA program is. Or if you're a game developer, you can write some cool special effect in CUDA and then show it on the screen. Okay, so we've been talking about CUDA, which is a particular way of programming NVIDIA GPUs, but like I said, it's actually the things that CUDA did well have been incorporated into OpenCL, which is a vendor-neutral way of doing the same thing. Right now, AMD CPUs and GPUs have an OpenCL runtime. NVIDIA GPUs have an OpenCL runtime. Intel has been talking about an OpenCL runtime. I can't remember if they've released it yet. They've been putting out white papers about it that will run on their CPUs. Apple, of course, released an OpenCL runtime with Snow Leopard that runs on Intel CPUs and NVIDIA and AMD GPUs, but their runtime is separate from the vendor runtimes that AMD and Intel and NVIDIA have put out. Also, IBM has an OpenCL runtime for Cell, and Imagination Technologies has been talking a lot about their OpenCL runtime, which runs on their new GPUs that are going to be in the next generation of iPhones and other mobile devices. Although I've been sort of overwhelming you with details about CUDA, I want to make the claim that the essential parts of CUDA are actually really broadly applicable and starting to be used in a lot of places. OpenCL's data parallel execution model is a clone of CUDA. So the way that you think about things is the same. Instead of calling it a thread block, you call it a work group. Instead of calling it a thread, you call it a work item. Instead of calling it shared memory, you call it local memory. But it's essentially an isomorphism between the ideas in CUDA's data parallel model and OpenCL's. OpenCL has a richer task parallelism model than CUDA does. So I didn't talk about CUDA's host-side task parallel model. CUDA, because I actually don't use it very often, but it does exist. CUDA does allow you to create streams, what they call streams, where you can assert as a programmer that a certain set of memory transactions and kernel invocations are independent of another set. This allows the runtime to pipeline sort of the transfers between the host and the device, as well as computation on the device. That can be pipelined instead of having barriers all the time. It also allows for multiple kernels to run simultaneously on the same chip. So say, for example, you run one kernel and it doesn't have enough parallelism to fill the chip. You can use another kernel in a different stream to fill up the rest of the chip. But I would say that OpenCL has done this better than CUDA does. So CUDA streams are kind of linear boxes that you, like queues that you stick stuff in. OpenCL, you have queues as well, but you instead encode a directed acyclic graph of dependencies between data transfers and computations, and you can enable out-of-order mode on some runtimes, on some queues, in which the runtime, instead of actually executing things in the order that you put them in, will respect the data dependencies that you declared, executing them out of order and potentially in parallel across the different devices that you may have. So, for example, you could use it for multi-core execution. You could, express sort of a tree of a DAG of dependencies and then let the runtime take care of what that actually means. So I think that's actually a fairly powerful task model that OpenCL has. Now, I do want to say to sort of put proper expectations about what OpenCL is. So some people propagandize, I don't know if they actually believe, but some people propagandize that OpenCL makes it easy to write parallel code for wildly diverse architectures, anywhere from multi-core Intel CPUs to AMD GPUs. I would agree that OpenCL allows you to use the same infrastructure and the same conceptual model for the machine that you're targeting, regardless of what it is. But the actual code is going to be wildly different. I mean, because the microarchitectures are so divergent, the kinds of parallelism that you need for a CPU versus a GPU are so different. These concerns bubble up all the way to the algorithmic level. It's very, very hard to write code that is performance portable across architectures. And just for an example, I wrote some code on an AMD GPU and optimized it. It was a reduction code, so I'm taking a big vector and then summing all the results. I got that to run at 80% of bandwidth limited performance on the AMD GPU, which I thought was reasonably good. And then I ran that code on the CPU and got some performance number, and it was 100 times slower than the CPU bandwidth limited number would have been. So then I rewrote my code for the CPU and got it to be 70% of peak performance. But they were completely different codes. As you might expect, I mean, for the GPU, I was launching on the order of 20,000 threads and having each thread do a sequential reduction as much as possible, but trying to launch enough parallelism to fill the machine, whereas on the CPU I only needed 4 threads to fill the machine as opposed to 20,000. So the code was completely different. In fact, on the GPU I needed to do parallel reductions inside of my thread blocks and then sort of write out the results. On the CPU, I didn't really need to do that because I only had 4 cores, so I just did 4 sequential reductions, and then I had 4 numbers, and then I did another sequential reduction across that, right? So the algorithm was completely different. The code was completely different. So OpenCL is a great way to sort of, with the same code environment, with the same conception of what parallelism is, to target different hardware. But it's not going to solve this algorithmic problem. So I just want to, the only reason I bring this up is because, as I read around on various fora on the internet, there's a lot of misinformed people that say, oh, well, if you had only written that in OpenCL as opposed to CUDA, then it would have run great on everything. And it's like, well, no, you would have had to write an OpenCL, and then you would have had to rewrite it several times in order to make it run great on everything. But at least you can do that. And so that is a great strength of OpenCL. It just needs to be understood in context. Also, I want to say that the OpenCL API is very low level. The triple chevron syntax for launching a CUDA kernel translates into about 20 different OpenCL API calls that you have to make yourself. So you have to make each of those things, each of the kernel arguments to a function is a different API call where you pass a pointer to the argument to the OpenCL API for each argument in the function that you're calling. So it's just, in CUDA has a compile model where you run a compiler, it tells you a compiler error message just like a C compiler would. OpenCL has a runtime model. You give it a string of code, then you ask it to compile. Then you ask it, were there any errors? If there were any errors, you ask it, how many bytes of space do I need to allocate to hold the error messages? Then you ask it to copy the error messages into the buffer that you allocated yourself, and then you manually print out the error messages from the compiler. So a lot of this can be automated and put in libraries and so forth. I'm just trying to give you a feel of, there's a difference in terms of the level of abstraction that these APIs present. So when you start OpenCL programming, don't be daunted by it. You can do it. It's not that hard. It is just very verbose. I'm going to skip this because of time. So I want to talk about how CUDA programs are actually mapped onto GPUs so that we can get good performance. So the idea is that CUDA is supposed to be functionally forgiving. The first thing that we want to do is to make things work, and the second thing that we want to do is to make it go fast. So you can write slow code, which is important to be able to do that. That's how we all get started, is write slow code. But then to get it to go fast, we need to understand every CUDA thread is mapped onto a SIMD vector lane. And SIMD lanes are grouped into warps, which are groups of 32 threads. It's a logical SIMD width. The hardware SIMD width can be something different. The thread blocks, each thread block is going to be scheduled onto a core, and it's going to sit there on the core until it's done. And in order to get peak efficiency, the hardware requires you to schedule multiple thread blocks per core. So you want to have the idea that you're sharing the resources of a core with multiple thread blocks. You want to oversubscribe. So the GPU is really pipelined. It's a throughput machine. We're trying to hide memory latency by having so many things co-resident on the same core that when one thing gets blocked waiting for a long latency memory transaction, we can just switch to another thing and do something useful. But that means that because we have so much state that we're trying to juggle, the performance that we achieve depends on how much resources each of the threads actually requires. If we have heavyweight threads that take up a lot of space, we're not going to be able to fit as many of them onto the same core, which means that we're not going to be able to hide memory latency as well. We're not going to get as good performance. So the more registers that your program uses, the fewer thread blocks you can fit onto a core, and the less performance you'll get. The more shared memory each of your thread blocks uses, the fewer thread blocks you're going to be able to fit on the core because, again, it's a shared resource. And so, it's often when you're doing CUDA programming, you're going to try to reduce your register count by changing the way that you do some stuff to try to get more thread blocks to fit on the chip. For Fermi, the magic number is 20. You want to get 20 registers or less per thread. And CUDA will tell you performance in terms of occupancy. I've put in some constants here on this slide for GF100, but for every chip, the constants may be different, so you need to look at the CUDA manuals. But the GPU is going to try to fit as many thread blocks as possible simultaneously onto a core. The number of simultaneous thread blocks, which I'll call B, has to be less than or equal to 8. That's an architectural constraint. The number of warps, which again, a warp is a collection of 32 threads, per thread block has to be less than 32. Or equivalently, the number of threads in a thread block has to be less than or equal to 1,024. The number of thread blocks times the number of warps per thread block has to be less than or equal to 48. In other words, each core can handle 48 warps in flight. The number, like I said, the number of threads per warp, which I'll call V, is 32. And then so the number, if you multiply all these out to figure out how much register state there is per thread block, actually per set of thread blocks that are targeting a single core, it has to be less than 32K. So there's basically 32K entries in the register file. And similarly, so that's the constraint on the register file. The constraint on the shared memory is similar. The number of blocks that you're scheduling onto a core times the number of times the amount of shared memory in bytes per block has to be less than or equal to 48K or 16K, depending on how you've configured the machine. And then, so once we have these constraints, the CUDA runtime will tell you the occupancy of your kernel is some number in between 0 and 1. That number is equal to the number of blocks times the number of warps per block divided by 48. So basically, how many warps did we manage to fit on the chip divided by its maximum capacity of 48 warps? So bigger is usually better. It's not always true. There are times, and Vasily will love to tell you about them, when, if you know Vasily Volkov, he's like a super amazing CUDA programmer. He gets really, really cool performance by playing with all of these things in really interesting ways. And he will tell you that, you know, bigger occupancy is not always better, and that's definitely true. But to a first order for beginning CUDA programmers, you know, better occupancy is usually better performance. SIMD and control flow. So this is always problematic. SIMD, you want to do the same thing for every SIMD lane, but control flow, you want to write code for each thread that's going to be mapped onto a SIMD lane, and you want them to be able to do different things because your program requires that for some reason. So the hardware, the GPU hardware and the compiler actually work together to manage divergence and convergence. If you have some of your threads doing one thing and some of your threads doing another thing, it's no problem unless you try to synchronize. So sync threads cannot appear in a divergent path. If you write code that says if thread index is less than something, do this and synchronize and then do that, otherwise do this and synchronize and do that, the machine will hang. This is bad. So, so you need to be aware of that. So the idiom then is going to be, if my thread index is one condition, do something, and if, you know, or else, you know, do the other thing. Then you end the if, then you do the synchronize, and then you open the if back up, re-diverge. So that's the way that you have to deal with synchronization. And in addition, good performing code will try to keep the execution convergent within a warp. So there is a performance penalty if you diverge inside of a warp. If you have different warps of your thread block doing different things, that's fine because each of the warps are scheduled kind of on their own. But if you break the warp apart and have some of the threads in a warp doing one thing and some of them doing another thing, you're going to start losing performance. So Kathy Yellick has this great quote, which I love, that a Manycore device is defined as whatever device that you have as a chip that turns a compute-bound problem into a memory-bound problem. I really love this quote because a lot of my performance concerns revolve around the memory subsystem and using memory bandwidth off-chip effectively. And you can sort of see why this is true. You know, if we think about the die photos that we saw earlier, or these cartoons of a die photo that we saw earlier, when we have all these different things that are contending to one DRAM interface, you know, memory concerns are going to dominate. I want to point out that memory is SIMD too. We talk about code, you know, execution of floating point instructions being SIMD, but memory is SIMD as well. So let's imagine we want to load word 0 here on pretty much any machine, an Intel machine, an NVIDIA machine. We're going to actually load not just whatever word we requested, but a set of words that are around it that we call a cache line, right? And it's going to be aligned to some place in memory, and it's going to be a certain width that's defined by our architecture. So this has two effects. If we have sparse accesses, we're going to waste bandwidth. So let's say that we are only interested in loading word 0 and word 4, and we're never ever in the rest of our program going to touch these other words. Well, that means that we end up wasting 3/4 of our bandwidth because we have loaded in 2 cache lines, and then we've used only, you know, 1/4 of the actual data that we loaded. So we don't want sparse memory accesses, and we don't want unaligned memory accesses. You know, if we load, for example, words 1, 2, 3, and 4, and we're never ever going to use 0, 5, 6, and 7 for anything else, so the cache won't help us. We will have wasted half of our bandwidth. So we need to think about these things on CPUs. We also need to think about them on GPUs. GPUs have sort of a device that's called a coalescer. It takes a look at the memory transactions which are coming from a warp and tries to stitch them together into a vector memory load or vector memory store. But in order to do that, it has the addresses that are coming from the individual threads in the warp need to conform to patterns that the coalescer can understand. The best thing to do is to try to keep your threads doing unit strided loads, and it'd be nice if they were aligned to the boundaries of the cache lines. So how can we make that happen? Well, we can pad our data structures, and we can store them in an order that is going to match the order we're loading data in our program. So for example, think about a multi-dimensional array, right? If you have a two-dimensional array, most of the time when you're going to write a program, you're going to think about how is this laid out. Memory is kind of one-dimensional, so you're going to have some layout that defines how elements of this multi-dimensional array are laid out in memory. So what you're going to want to do is make sure that you think about adding padding elements. So if you know you're going to have all of your threads accessing here and then all of your threads accessing here, you may want to add some dummy elements to the end to make sure that this row is also a multiple of 32 elements away from the beginning of this row, so that they're always going to be aligned. And you're going to want to make sure that they're as dense as possible. And let's see, I'm running out of time here. But here was a real-world example that I worked on, which is a sparse matrix vector multiplication kernel. You can see this is a multi-diagonal matrix. And the question is, how am I going to represent the matrix? I'm going to be doing a lot of these sparse vector, dense vector dot products, where I sort of march down a row and march down the dense vector to come up with an entry in the result vector. Is there a structure that I can take advantage of in this matrix? Well, I realize that it's diagonal. So maybe what I could do is represent each of the diagonals as a single vector. That way it would make the matrix really dense. And so that's what I did here. I took the matrix and I sort of projected it down into a set of 5 diagonals. And you can see like these elements are empty because these corresponding elements for that top diagonal are also empty. So I made this dense data structure, and so that should give me better performance. Yeah?
So diagonals map to rows and columns map to columns.
Yeah. That's right. In this particular projection. That's what I mean by this sort of downward arrow, that I'm sort of projecting the columns down. So I launch a thread per row. Well, am I done? Well, it turns out that the straightforward diagonal projection is not aligned, even though I've made it dense. So I have one thread doing here, and then going here, and then here, and here, and here. But even though I'm loading a dense set of vectors each time, they're not going to be aligned because they're sort of jumping around because of the projection that I used. So what about if I projected it a different way, where basically I'm sort of taking them, and you can think about it as sort of skewing it, shifting it so that this row, instead of starting here, this row starts here, and this row, instead of starting here, is there. So I've kind of skewed it. This actually will ensure that all my memory loads are coalesced, as long as I insert some padding to make sure that it's a multiple of the cache line size of the machine that I'm targeting. So let's see. Another common thing to do is to deal with structures of arrays and arrays of structures formats. So if you have all of your threads loading an element, say you have a struct with 3 elements, x, y, and z, and you have a vector of these structs laid out. So in memory, it's going to be looking like x, y, z, x, y, z, x, y, z. If you have each of your threads loading element x but not loading elements y and z, we're going to have a sparse memory access pattern, and we're going to lose performance. So to get around that, a lot of times it makes sense to transpose the data structure. Instead of storing it as x, y, z, x, y, z, x, y, z, we have one vector of all x and one vector of all y and one vector of all z. And that is called structure of arrays format. Now, when we do that, if all of our threads just access x, it's okay because we're still going to have a dense memory access on our x array, and then we just will never load from the y and the z arrays. So that's something to think about with your data structures. It's often worth the cost of transforming your data structure from one place to the next in order to ensure better memory accesses. And I'm out of time, so I'm just going to conclude. I've had a lot of fun programming in CUDA. I think one of the best things about CUDA is that it's really tangible. You can sit down and write a parallel program and see it going faster, right? Parallelism, you have to make it go fast in order to, feel like the effort was justified, right? In CUDA, it's actually really easy to do that. hopefully I haven't scared you off too much with the complexities of CUDA. There's always a lot of things to learn, but it's not so bad, and it's pretty easy to get started. If you have any questions, I know Michael is a pretty good CUDA programmer, so I'm sure he'll be able to help you out. And if you want to talk about CUDA stuff with me too, just send me an email. So that's it. Thanks.
Special because of the upcoming assignment in this yet new language, or just going to do whatever's necessary in office hours? I guess the question is, is there anything more material in your slides that should be covered that you didn't have a chance to do?
No, the rest of my slides were mostly just talking about things I've done with CUDA and things my friends in my group have done with CUDA. So I've covered all of the material that I meant to cover about the language itself, but there's still a lot to learn for all of us. So.